Is it? Can you hear? Okay. So last lecture, and I will try in the very end to summarize. Let's see if Rogerio will let me summarize. In fact, if I will be efficient enough to get there, that's not Rogerio. So I would like in the very end to summarize, but what we've been doing, we've been discussing the structure of a theory with scalar fields like the standard model, focusing on the standard model. And we started this session with talking about one important, maybe one of the most puzzling and central questions in particle physics and cosmology, which is the vacuum energy density of the universe. And we discussed that it's related to the vacuum structure of the theory. The vacuum structure is highly non-trivial, thus not answering any aspect of this question, just unfolding maybe additional parts of it that are puzzling. How do I turn, which one? This one. That are puzzling. And I'll talk about this a little bit more today, but then I also want to talk about some other puzzles that I've mentioned in the very first lecture. And the puzzle I want to discuss will be dark matter, as you can see. Most of what you see there is dark, and you will see this is related to dark matter. And because I've been talking so much about scalar fields, I'll connect the question of dark matter to scalar fields. You'll hear much more about the particle physics, particle cosmology, and other properties and models for dark matter later on in the lectures by Nicholas. But we will try to make the connection to the scalar fields that I've been talking about. But before I do this, when you talk about dark matter, all of you know that we have this question about dark matter, and people mention rotation curves and CMB and cosmology and whatnot. But I wanted to just start this with a short motivational discussion. I would like to give you a little data set that is easily accessible, whereby you can convince yourself, if you walk just a little bit, that you see this evidence for dark matter. Right? So when we talk about, for example, the structure of CMB anisotropies or large-scale structure, these are perhaps, these cosmological evidence for dark matter are the most, if you want, robust and clean and theoretically beautiful and precise ways to see and quantify dark matter, but are quite difficult to compute. It would take me a course to kind of derive the machinery to do it. Once you have it, it's very clean and nice. Galaxies, like this one here, on the other hand, are much more difficult to calculate precisely, but they can allow you to understand the order of magnitude of the problem very easily. So before I go and show you some models of how you can make dark matter and how some particle physics theories produce for you dark matter, let's just convince ourselves that there is dark matter and understand what we're talking about. It will take probably 15 minutes or so, depending on your interest, and then we go back to our calculations. So who knows what this galaxy is? Which galaxy is that? Somebody must know. The nearest neighbor to the Milky Way that is essentially as big as the Milky Way? Andromeda, thanks very much. Andromeda is so close and so big that you can see it with the naked eye in the clear sky or just with binoculars. You don't need much. This is with a very simple amateur telescope, I think this is taken. The size of this smudge on the sky is as large as the moon on the sky in terms of the angular size. But it's very faint, so it's hard to see. This is why you need a telescope, not to make it big, just to get enough photons concentrated from that region. So that's Andromeda. And before I even mention dark matter, Andromeda is very nice because you see Andromeda is related to a big puzzle in cosmology that people had. And the key to solving that puzzle was Andromeda. And I think there is an important lesson potentially to learn from how it was done. So just in a couple of slides, what is the first cosmological puzzle that was solved by means of looking at this Andromeda? And so you see, people were aware of Andromeda for at least 1,000 years. It appears in Arab astronomers or astrologers. There was somewhere in between texts, but written texts describe Andromeda at least 1,000 years ago. And what they didn't know, they noticed that this wasn't a star. What they didn't know was how far this thing was and what was it. And so for at least 1,000 years, humanity was fully aware about this beast in the sky, but had no clue what it was or where it was. Okay? Here is a big puzzle for you. And in fact, it took these thousand years, and only about 100 years ago, actually almost precisely 100 years ago, humanity, sorry?
Next year is
100. Okay. But I think it was officially solved a few years, or informally solved a few years before that even, so a year ago, actually, 1923, let's see. So this problem was solved only 100 years ago. And if you want the qualitative lesson to keep in mind, is that it was solved not because people got particularly smart. It's not that they were much smarter than they were 1,000 years before, but it was solved because we developed the correct technological tools, and we were observant to see, some of us were observant, some of them, to learn some features from these technological tools. So the person who solved this, and I think the date is 1923, although the paper is later, is maybe even 6 years later, the official paper. You can check, Roger can check. But I think the measurement was dated to 1923, a measurement by Hubble that in trying to understand the distance to Andromeda was looking, or in other features of Andromeda, was looking at it in a telescope, and he realized that there was a pulsating star in Andromeda. And look, Hubble was not a particular genius in this respect. Hubble simply had the largest telescope that there was in the world at the time of these observations. So a new technological breakthrough. People kept on looking at this object, trying to understand what it was, and eventually the telescopes became strong enough that people could identify pulsating stars, like this Cepheid that Hubble saw in Andromeda. You put this together, the date here is wrong, sorry, that's a typo. Henrietta did it many years before. So what was known, and the reason that Hubble understood that he struck gold when he saw that Cepheid in Andromeda, was the fact that Cepheids are standard candles. You can find out the distance to a Cepheid without even knowing much about it. Basically, you can guess its intrinsic luminosity without knowing the distance. That's the right way to do it, to say it. And the way this is done is that, you remember before, this star is pulsating in time, and if you measure for many of these stars the period of the pulsation, this is log 10 of the period in days of the pulsations for these stars, as a function of the intrinsic luminosity of the star, magnitude, because these people are astronomers, but intrinsic brightness of the star, then there is a positive correlation that is pretty narrow. Why is this good? It's good because when you look at something very far and very faint, you really don't know the distance. You don't know in principle the intrinsic luminosity, but what you can easily measure is period. Right? Doesn't matter how dim, if it's bright enough that you can measure the period, that's great. You got the x-axis. From the x-axis, you can calibrate what is the absolute luminosity of the thing. Now you know the luminosity at the star, and so from the observed luminosity, you can get the distance, similar to what we did with the supernova exercise. So it's a combination of observing the properties of systems, learning more and more about them, and using the biggest telescope there was at the time that helped to solve this problem. I think this is a good thing to keep in mind when we think about dark matter. You really will hear a lot about particle physics models and ideas for dark matter, but at the bottom line of this story, it might be that we still simply don't have strong enough telescopes, or strong enough observational tools, or that we didn't understand well enough different properties of the systems we are looking on. But the key is to go on, potentially, is go on and look for more of these kind of clues that you can use in technological advancement. So it might be that we still didn't have the correct device to understand what it is. Then, of course, the evidence for dark matter came from measurement of the rotation curve of galaxies like Andromeda. This is the original paper, I think, of Vera Rubin and Kent Ford on this rotation curve of Andromeda with the original data. So what they're measuring is, through the Doppler shift, they're measuring the velocities of clouds of gas and certain types of stars in the disk of the Andromeda galaxy as a function of the distance from the center of the galaxy. So this is velocity in kilometers per second, about 200 kilometers per second, at distances of some, we will see later, some thousands of light years from the center of the galaxy. This is a paper from 1970, but it's very easy to go, just Google measurements of these velocities. There are many attempts to measure these velocities of rotation. So that's a compilation of recent measurements. I replaced the x-axis instead of units of arc or minutes of arc, so angle on the sky. I replaced it with absolute distance, now that we know the distance to the object. And so you see that the measurement of Vera Rubin is actually very good. We agree with it even today. Nothing really changed. Well, nothing really changed at distances of some 10,000, maybe of order 10,000 kiloparsec. What did change, thanks to technological advancement, is the fact that we can do other things now. We have much stronger telescopes. This is an image from Simbad. It's a database that's available to all of you. You can just Google it and get pictures of galaxies and analyze them, scientific pictures from various different telescopes. So I got this one for Andromeda. Here is the link. And what I show here, this is the actual galaxy as seen by the telescope. And I put a ruler of roughly 30 kiloparsec, roughly measured by eye, on this map. And so here are the measurements by the old measurements, essentially by Rubin, or recent measurements that agree with Rubin, and they go roughly all the way to the end of this red line. So as I was saying, what's really changed is the fact that now we can measure objects that are much, much fainter and much farther away from the center of Andromeda. So this is just a zoom out, and you see I go out all the way to 300 kiloparsec here. So 300 kiloparsec is roughly 1 million light years away from the center of the galaxy. And again, I put very rough illustration of the measurements that there are today from this summary. There are other summaries out there. Now, the details are not very important for us. The error bars are mine, very conservative error bars, mostly systematic. But the key thing is that the velocities really drop very little. Here is the scale. They drop very little. The rotation curve is basically flat all this way far away from the galaxy. So that's an example, interesting rotation curve. And I think the most striking thing is after you put this picture together, again, very easy to do, is that you see these rotation curves measure velocities of objects over here. They are essentially not stars. Some of them, the nearer one, are globular clusters, so bunches of many stars together. Some are even dwarf satellite galaxies that are flying around Andromeda. So very faint and far away objects. They're flying in this void very far from the galaxy. Nevertheless, they're all bound to this tiny little speck of light. This is what it looks like. So stuff here still flies away. This little speck of light dominates the gravitational potential all the way to this distance. This is an amazing thing that you can see just by combining these measurements. And now you can analyze this quantitatively with very simple tools. So just to see that it's very easy to understand the rotation curve property of a galaxy like that, you don't need very sophisticated techniques like in this paper or modeling like in this paper. So for example, here I test myself that I understand what's going on. These people determine parameters, structural parameters of Andromeda. Here are two important parameters. One is called M200, and the other is called R200. These are names that you will encounter in cosmology. R200, the meaning of it is just as follows. So if you calculate or if you measure, or in your model, if you want, of the mass distribution of this object, this system, well, the model says that the density, mass density, is higher in the center and decreases outside. R200 is just the distance from the center at which the density of the object becomes roughly 200 times the cosmic average, right? So we live in an essentially very void universe, very low background density. Galaxies are these clumps of mass. And this mass estimate from the complicated model says you have to go 200 parsec, that's the circle that I put here, for the density to drop to 200 times the cosmic average. You have to go more to reach the cosmic average potentially. Okay? Confusingly, for Andromeda, R200 is roughly 200 parsec. There is absolutely no relation between the name R200 and the 200 parsec for Andromeda. For example, for Fornax dwarf galaxy, R200 is about 10 kiloparsec-ish. Okay? So please don't be confused about that. So now to see that I understand what's going on, you see in the simplest model of this galaxy, there will be a blob of mass, roughly spherical. We are looking at things that are moving around at some distance r. And we're looking at different things at different distances. This plot describes the velocities in a model that is very simple, so just circular rotation. For a circular velocity around the mass m of r, if there is a mass distribution m of r, then the circular velocity should be g m of r over r. Life is more complicated if the velocity is not circular or the mass is not circular or the mass is not spherical, for example, but to small corrections, this is the exercise that you need to do. So this means that if measurements give you the velocity and they give you the radius at which they found the velocity, right? What do I have? I have velocity as a function of radius. So I know r and I know v. And so I can get what m is. It means that m of r is v squared r over g. OK, let's check if very simple estimate, m equals v squared r over g. If this agrees with the estimate of the complicated paper, just put the numbers in. Here is the fat data point is 200 kiloparsec. And what comes out of the box is 10 to the 12 solar mass, which is very compatible with what the sophisticated analysis does. So you see, so within 10, 20%, you don't need to think very much. You can see this. So we can measure the mass of this object. And again, what we're measuring is roughly the mass inside of the orange circle. OK? So far, I really recommend that anybody, whoever is going to work on dark matter, will understand our nearest neighbor, Andromeda, and do this little exercise. So we found a bunch of mass, 1 trillion solar mass. How do we know this is related to dark matter? How do we know this is not something like stars or gas? Well, what you are going to do is you're going to try to understand, well, how much mass is there in stars? If there is 1 trillion mass in stars, forget this dark matter story, right? And so you try to model the stellar emission or the stellar mass. Now, we see the stars. Here are the stars, this tiny little speck there. And I should tell you, modeling how much mass there is in a distribution of stars is incredibly difficult today. It's really very difficult. We're not very good at it because we don't understand from first principles what stars do. That's one. And second, usually we only see a fraction of the actual stars that are there, the brightest ones, not necessarily the ones that give the most mass. And so here is an example, again, from our sophisticated model. What you see here is the distribution of light in Andromeda. Notice the scale, distribution of light out to a distance of about 20 kiloparsecs. So it's really deep inside of that light blob over there. And you can see the ellipses. The ellipses are measuring basically the percentile of mass that is of stellar light, sorry, that as you go from the center of the galaxy. That is, just measure how much light these stars are making. In here, most of the light comes from. Here, there is a little more, and here, there is a little more. I'll put the numbers in a minute. Now, so you measure all this light. Measuring light is not so hard, but as I said, converting light to mass, that's the thing that's really hard. And indeed, in the sophisticated model, or in the sophisticated paper, here you see different estimates for how this light that we measure so well maps to mass. Stellar mass, mass of stars, the thing you would think we know. And notice the following thing. Just when you look at it, and this is just a nice example, you see the things here on the left, on this column, the names are just names of models of stellar populations for Andromeda that we're trying to guess which stellar population model is correct for Andromeda or not from all the observational information. All of these are more or less consistent with everything we see as far as we understand theory. Look at these numbers. These numbers here are basically telling you, for a given stellar model, what is essentially the mass-to-light ratio of that stellar model. And you see, one model that is perfectly fine in terms of all the observation information gives you this number 5, and another gives you a number 11. Okay? What to take from this? To take from this, even if you see stellar light, you really don't know how much mass there is there to a factor of 2, sometimes to a factor of 3 or 4. Even Andromeda, by far our nearest neighbor, better understood than us, than our Milky Way galaxy. So that's really hard. We can't really tell clearly what the stellar mass is or baryonic mass is to better than a factor of 2 or 3. Where is our luck? Why can we even say something about dark matter? The reason is all of this complicated discussion, it all has to do with this tiny little blob inside. But if you actually ask yourself how much or where does this stellar distribution where is it, in fact, spatially? So here I put this yellow line from one edge of the furthest ellipse to the other. This furthest ellipse contains 95% of the light. The one before is 90% of the light. And then I put the same line to scale in the drawing. And so whatever these stars are doing, they are all of them essentially in this tiny little speck of light, and there is none of them outside. And so whatever the stars are doing, I don't know the stellar mass to a factor of 2 or 3, but it's all essentially a point mass with respect to this large-scale distribution of the galaxy. And so I can look at the shape of the rotation curve. I'll skip this. This is just a constraint on the gas. So back to the complicated model, now we understand we actually don't care so much about the details of the stellar model. If you look here at the velocity as a function of radius, data are the measurements, r is the distance from the center. We know now, so the dotted line is the stellar mass, and we know now that the stellar mass, or the stellar induced velocity, you see the stellar induced velocity after about 20 kiloparsec, it just decays like the velocity from a point mass. And so you can lift it up or down by, say, 50 kilometers per second. You can lift the dotted line up or down because we don't know much about it. But even if you lift it up or down by 50 kilometers per second, it is very far from addressing the actual velocity that you measure. Okay, so there is shape information. The velocity curve just decays much, much slower than what the stellar mass is doing. Okay? And so this is an exercise really very easy for you to do. If you do it, you find within, say, 50% uncertainty that inside around about 30 kiloparsec from the center of the galaxy, stellar mass and dark matter mass, or unobservable mass, or unobserved mass, are roughly equal as far as the rotation curve cares. This can move a little bit. You can move the dotted line a little bit, but far out at a few hundred kiloparsec, dark matter dominates. And if you work it out, a jump of a factor of 3 in velocity, you see a factor of 3 in velocity is a factor of 10 or a factor of 9 jump in mass. Okay? So this mismatch by a factor of 3 is roughly a factor of 10 in mass. There is roughly 10 times more mass in Andromeda than there is stellar or other baryonic mass, and it's an exercise you can easily do. So that is the puzzle that we have. That's a puzzle that you can explain, to your children. And I like to work on something that I understand, that I can explain to my kids if you want. And now our task is to understand what this is. Okay. So, and here is the problem. Maybe you will feel it also when you start the lecture series on dark matter. The problem is, from the particle physics point of view, it is insanely easy to make dark matter. We have a puzzle. We don't know what this extra mass is, but it is trivial, essentially trivial, to write a particle physics model that does it. For example, I think Nicholas can correct me if I'm wrong, but you will get examples where dark matter is the following idea. You take the standard model of particles with its fermions and leptons and hadrons and neutrinos and whatnot, and you just add another one that's essentially very similar to them. For example, the first guess of humanity was, let's add something that looks like a massive neutrino. You do this, it's dark matter. Okay? You couple it a little bit to the standard model, adjust the couplings a little bit, and you're in the game. In fact, neutrinos are dark matter in the standard model. Standard model neutrinos are interacting feebly enough with light and everything else, so they will not disturb rotation curves and cosmology and so on. The only problem is, and in fact today they are non-relativistic. The only two problems are that they are slightly too light, so they were still relativistic at the time that we know structure should still be growing, redshift of, say, 10 to the 4, 10 to the 5, they're relativistic, that's a problem. And the second thing, there is not enough of them. So today they're a small contribution to dark matter, but because of this little technical silly point, they cannot be the dark matter of the universe. But if you took the mass of the neutrino, for example, in some seesaw model, there would be a new Yukawa coupling that's proportional to the mass of the neutrino. You just move this Yukawa coupling up by a factor of 100. We think it's very small. Move it up by a factor of 100. Neutrinos of the standard model are dark matter. Okay? It's that easy. Of course, the details of the model will dictate how you're going to try to look and search for it in the laboratory. in that sense, it's very important to try to think of different models so we can try to cover as many ways to search for this particle as we can. But as of now, we don't really know what we're looking for. So my plan for the rest of this lecture is to show to you that our nice scalar field that we've been playing with all along with some potential v of phi, for example, some potential that does something like this or whatever, also can be dark matter. Not the Higgs, but a simple generalization of the Higgs could also be dark matter. Yes?
I'm sorry I've asked this before, but the measurements are far away, like 300 kiloparsec. How certain are we that they're gravitationally bound to the galaxy? Just because it seems non-trivial a bit.
It's not trivial. And so there are observational uncertainties. It's a very important question. Moreover, these objects at 300, 400 kiloparsec away from the galaxy are really usually not part of the disk. You know, the disk is this little thing at, say, up to 100 kiloparsec. But when you look at 400 kiloparsec, these things are moving wherever they want, usually not on circular orbits. So there is a little bit of analysis to cast the information in terms of effective circular velocity. That's all I'm going to say about it. Okay, so but there is analysis to do. So what you see is line of sight velocity. If you're lucky, you have a little bit of parallax. For this system, usually not. So you have line of sight velocity, and you need to try to model the orbits of these objects and hope that you have enough of them. You can do it. For Andromeda, you have enough of them. And for many other galaxies, you also have enough of them. And also, if you go just to 100 kiloparsec, situation is much better. For example, in the Milky Way, which has a very similar structure to this, we can do parallax up to 100 kiloparsec. And so we can really measure, and we're looking at stars there, not just satellite galaxies and so on. So we can put the picture together, and it holds. But it's non-trivial, not to make you think that this is trivial. The trivial part for this exercise was now let's take the velocity measurement from the observers and understand the theoretical implications, okay?
Mm-hmm. Okay, thank you.
Yes.
How you can say that it's kind of black holes or dwarf stars, things like that, something black, not kind of particles. I mean, to me, it's good to be particles. I'm a particle physicist, so.
No, but the question is not what it is to you. It's
yeah,
what it is.
Yeah, but
so
how can you say that?
It might be black hole. It might be stellar remnants. So, for example, I guess the key question is it a part of the standard model, or is it something totally new? Stellar remnants, like black holes and neutron stars, are in a way part of the standard model, right? It's the end of the life cycle of stars. There are also things in the beginning that are called brown dwarfs, things that didn't quite turn on. Here is the thing. Stars make these stellar remnants and these failed stars. They're all related to star formation. So when you have some population of stars, in some galaxies, suppose you have some population of stars as the mass of the star and the number of objects. So in some region, say from, I don't know, roughly 10 to the minus 3 times the mass of the sun, up to a few hundred, or maybe 1,000 times, so 10 to the 3 m sun, these objects will be stars. And so we will see them. We poorly understand the formation mechanisms that cause a cloud of gas to form this or that, or in fact, usually a cluster of many stars with many different masses and a mass distribution. We poorly understand that. Not to mention, we poorly understand the formation mechanism of these things and these heavier things that maybe do direct collapse black holes or tight clusters of stars and so on. All this spectrum exists. It is probably continuous. It is observed to be continuous, in the part that we can see it. But the thing is, the spectrum of masses, and again, these details that we don't know are the cause of this factor of 2, factor of 3 differences in mass to light estimate, okay, that I showed you before. The thing is, all of this chemistry is happening where there is gas, and all of this chemistry is causing some stars to occur. So yes, it's possible that stellar evolution models make a lot of black holes, for example. It makes a lot of very massive stars that very quickly go to black hole. And so it's possible when you see a gas of stars that are actually many invisible, 10 solar mass black holes flying in there, coming from direct collapse. And a bunch, and there are, by the way, many neutron stars in there, of the order of 1 or 2 solar mass, 1.5 or 2.5 solar mass that are flying there with the stars, and you don't see them. They are dark remnants. However, they live together with the rest of the zoo, if you want. They're the ticks on the elephants, if you want, or the elephants on the tick, I don't know, depending which way you look. But they're all together in the zoo. We've seen where the zoo is, right? We've seen where these stars are. Stellar evolution models produces all the rest, but they will live together, okay? The fact that all of these dark objects exist together with the stars is important, and it's part of the reason that if you look, for example, at what these people are guessing, oops, yes, here, great. Look at this. Look at, you see, this column. You can go back to my slides later, but you see, this is the ratio between mass to light in some band, okay? But you can sum it together. So roughly mass to light. You see the ratio between mass to light is 10, of order 10. There is much more mass than there is light. This is precisely because in this model that is essentially a guess or a chemistry prescription or a cookbook of how much of everything is, there is much that you don't see. It doesn't give you light. It's in there. So in that sense, you are safe. Unless, so you need to be in some, the chemistry is the chemistry wherever you are, so where it acts, it also makes stars that you see. So that is the argument why, at least I'm not so worried about this possibility. Maybe what you meant is that dark matter could also be something that is not so much a particle. It could be some kind of primordial black hole. Certainly, this is in principle a possibility. Then I hope it's not a stellar mass, because that would be very wicked of the universe, to make dark matter black holes that are there from very high redshift have the mass of black holes that stars make, right? Why don't you make it the mass of black holes that are 10 to the 10, the mass of black holes that stars make, or 10 to the minus 10, right? Why just the thing that will confuse me? But maybe that's what it is, right? I don't know. So that's a possibility. I won't speak of it. Maybe somebody else will speak on it. I will do something totally different. I will just claim it's so easy to make dark matter that our funny little scalar field, possibly the simplest model of dark matter, already tends to do it, or more precisely, can easily do it. This can easily become a model of dark matter. The way we looked at the scalar vacuum structure so far, we mostly asked ourselves what happens when there is a scalar stuck at some point, for example, here in the very early universe, or for example, here at the bottom of its potential today, as far as the Higgs field is concerned. And we know that this is a contribution to the vacuum energy and discussed it a lot. For the scalar field to be dark matter, it actually needs to be moving around. So it needs to be moving along its equation of motion in some non-trivial way. What I will argue is that this motion is quite simple to understand. So we want to understand the physical properties of this object with this energy momentum tensor that I quickly derived yesterday. And the first thing to note about this energy momentum tensor, a comment on the side, by the way, ask me later, I'm going to solve the classical equation of motion and consider the classical contribution to the energy momentum tensor. So I'm going to neglect quantum corrections on this. You can think about quantum correction as if they're effectively inside V, but that's just part of the story. There are quantum corrections that could be relevant that I'm ignoring, and I hope I have time to discuss maybe in the Q&A. But notably, what I'm doing is classical. So classically, we have this energy momentum tensor, and a surprising thing about it is that it is, in fact, describing a fluid. Okay, so when you talk about cosmology, you often think about cosmic fluids, right? And so cosmic fluid, what's the point? Or we think about a perfect fluid, more precisely, in the homogeneous isotropic limit. And this object is exactly one of these objects, is a perfect fluid, in fact. So this object is a perfect fluid. How do you know whether some energy momentum tensor describes a perfect fluid or not? Physically, the thing about perfect fluid, and you can get it in many different physical ways, but the thing is, you see, when you have some substance with energy and momentum and flow, things are flowing around, it is a perfect fluid if there exists a frame of reference. Subject to it, if you describe this fluid at every given point in space and time, if you choose a frame that is moving together with the flow of the fields, think of some river that is flowing. You throw something in this river and it flows with the field, then the only thing you see are energy density and pressure. These are allowed to be different. These are two numbers describing the fluid. They will depend on the microphysics of the fluids, but these are the only numbers describing the fluid. In the back of your head, you should understand there is another vector of numbers, which is the velocity of the flow that you use to put yourself to flow with the river. These are three additional numbers that describe the flows. But once you find this velocity, if you boost to it and sit on it, all you see is energy, momentum, and pressure. This is very non-trivial, right? Many substances don't satisfy it. For example, a gas of collisionless stars in a galaxy do not satisfy this condition because it absolutely can have crossing streams, right? There can be some cloud of stars coming from this direction, another cloud of stars coming from that direction. They're crossing each other. Stars are essentially collisionless because there are so few of them. They just pass through. And so what is the frame I should look at now? There is a stream here, there is a stream here. Where should I be looking? There are crossing streams. There are non-trivial, basically multiple moments for the momentum flow of this system. A perfect fluid doesn't have it. It doesn't have crossing stream. If streams meet, they have to merge and give you a unique velocity that you can sit on. That object actually does have it. To see that the energy momentum tensor is a perfect fluid, you just need to check that you can write it in some particular form. If you can write it like that, then it is a perfect fluid. This description has two scalar functions, P and rho. This will be the energy density and the momentum. And the 4 vector, because we're doing relativistic dynamics here, which is u mu, that is normalized. This u mu in my convention is +1. And so you can think about this u mu as something like gamma times 1 beta, normalized relativistic 4 velocity, but now it depends on space and time. This thing is flowing. But at any given point, there is a gamma and a beta. You can boost to this beta, and then you can boost. If somebody gave you this 4 vector field, you can boost to a frame where u mu is just 1, 0. And that would be the comoving frame of the fluid. So it's an easy check to see that you can do that. And the exercise that you can do yourself easily is that here, let me just explicitly construct these functions. Here they are. Rho is this. P is this. And u mu is this. In other words, what is the primary object for which this energy momentum tensor is defined? This primary object, the physical object, is just a scalar field configuration phi of x. The energy momentum tensor tells you what is the energy density and momentum and so on associated with this non-trivial field configuration. You can take this phi of x, construct these objects, the 4 vector and the rho and p, and just put them back together, and you will see that they construct mu nu this way. That's all you have to do. Once you've done that, you can see that there is a comoving frame. Well, in this comoving frame, u mu is 1, 0. And then in this comoving frame, T mu nu phi, the comoving frame, let's say, is just so. Let's see. The 0, 0 component of this has 1, 1, because it's 0, 0, so it has rho plus p. My metric in this comoving frame will just go to the eta metric, eta mu nu, and so it's going to be just 1 on top and minus 1 on the space diagonal, so it will be p plus rho minus p, it will be rho. And if you do the II indices, so the II indices of this object vanish, and my II indices of this object are -1, so I get P. Excellent. Which is exactly the energy momentum tensor of a perfect fluid in its co-moving frame. Good. Nice for us. Again, I made this comment briefly yesterday. Notice that those trivial configurations of the field where it is just stuck at a point, at a minimum of its potential, they have all the derivatives vanishing. So this is 0, this is 0. Here you have to be a little bit careful, but if you do this math carefully, you see this, what is written here is actually P minus P plus rho, and it doesn't go to 0, it just gives you a constant. So be careful a bit about the singularity, but there is not, in fact, if you do it carefully. And so in this co-moving frame where the derivatives are 0, then you see that if d phi by dx alpha is 0 for every alpha, then P, then rho is minus P, and it is V, and that is exactly a cosmological constant. But now we are going to care about what happens when this field is moving around. To see what happens when the field is moving around, we need to solve its equation of motion. Finally, actually solve it. So we need the equation of motion. I wrote the action yesterday. Take the functional derivative of the action with respect to phi to find the equation of motion. This is what you find. Equal to 0. So that is our equation of motion that we're going to need to solve. I will solve it very quickly. In the regime where we're looking at homogeneous and isotropic universe. So in a homogeneous and isotropic universe, in particular, this energy momentum tensor is also homogeneous and isotropic in the limit that I solve it. So in this limit, my metric was 1 diag minus a squared. So minus g is absolute value of the determinant of g mu nu. That was a cubed. Now, all space derivatives have to vanish. You can only have dependencies on time through the scale factor a of t and through our field, which degenerates to phi of t, because we care about homogeneous isotropic solutions. No spatial derivative, but we can allow time derivatives across time slices. So in this limit, of course, the equation becomes much simpler. In this limit, the equation becomes much simpler. So I have the square root of the determinant. This is 6. You should have corrected me. So it's a product of all of these people. So it's a to the 6, absolute value. And the square root of it is a cubed. So I have 1 over a cubed from the square root. I have d by dt, because that's the only derivative that can be non-zero. Here I have a cubed, which is this. And here I have g00, which is 1 in this frame, and phi dot, d phi by dt, plus, let's call this v prime, equal to 0. That's all I have to solve. So we can solve this. This tells us that phi double dot plus 3 a dot over a phi dot plus v prime, phi double dot plus 3 Hubble phi dot plus v prime is 0. This is the equation of motion we have to do. questions? Who has seen this derivation more than once? No, come on, you're being nice. Okay, but not too many of you, actually. Very few of you, actually. So this is the object that I have to solve. And let's just solve it. So to solve this equation, I need the potential. Let me make my life very simple. As I told you, I want to give you the simplest model for dark matter in the scalar field. So let's just imagine a situation where the model is such that the nonlinear features of the potential are very small. They are very small for the evolution of the field in the vicinity of some minimum. Obviously, this is just some particular limit of the possibilities that this kind of models can have. Okay, but that's an easy limit that is easy to solve. So suppose we are near enough some minimum. Let me also choose this point to just call it phi equals 0. If phi was not 0 in your previous basis for phi, at this point, just shift it by a constant. And so I will call this the origin of field space. Why not? And now my field is somewhere here, and I want to understand what it is doing. And I'm going to make another point. I'm going to make that the initial condition for the motion of the field is such that the first derivative of the field, so phi dot, when I start time, right, when early hot Big Bang begins to evolve, the initial condition is that the derivative is 0 in the beginning of time. This is a very natural initial condition as far as inflation or slower inflation has to do. Okay? So it's natural to start with phi dot equals 0. And then we will just try to solve this equation of motion. So near the minimum of the potential, I will just approximate v of phi very roughly as just the m squared term. If there was some lambda term, some phi cubed, phi to the 4, and other powers of phi, near the origin, they're smaller compared to the mass term. In general, they will be there. You need to worry about them. They're not a huge deal for us, as long as this approximation is roughly right. Okay, that's enough for us. So I will do this. This is very weakly. How do you write weak? Weakly interacting. Some models, like axion models, can naturally produce this situation. Other models not. Okay, but that's what we will look at. So if I do this, then v prime is just m squared phi. So that's the first thing I need. So the equation of motion that I have is phi double dot plus 3h phi dot plus m squared phi is 0. Okay, the next thing I need to say something about this Hubble parameter. Let's do this exercise. So we can do this exercise for different values of Hubble parameter. So at some point, it could be the case that the evolution of a scalar field is the dominant source of energy density in the universe. This would be the case in the matter-dominated area of our universe if this field is actually the dark matter. For example, if it is axions and axions are the dark matter, there will be a range of time where, in fact, age is coming from matter-dominated dynamics. But even for axions and for many other models, radiation usually dominates early on. So we can do it in general. We can say, to make our life easy, remember we need the Friedmann equation, rho, to understand how age behaves as a function of time. Let's make my life easy and assume that rho is dominated by one substance. Later on, it could be my field itself. Early on, it could be radiation, but it is one substance. So suppose that A is proportional to A to scale factor A, rho proportional to scale factor A to the minus n. For example, in radiation domination, we already saw in the first lecture that n would be 4. And in matter domination, we know that n would be 3. And somewhere in between, it will be somewhere in between. Okay, so let's do this. This equation says that A dot over A is proportional to A to the minus n over 2, the proportionality factor is going to end up unimportant for what we need. Okay, so I just take the square root of this object and I ignore proportionality factor. And so it says that a to the n over 2 minus 1 dA is proportional to dt. Okay, I just move this thing to the left and move the dt to the right. That's all I'm doing here, which means that this is proportional to dA to the n over 2. And so A of t in this kind of epoch, A is proportional to t to the 2 over n. Okay? Because of that. Once this is true, and now you see why they didn't care about the proportionality constant, because the only thing I really want is the Hubble rate. And this says that the Hubble rate, which is A dot over A, any proportionality constant would have canceled in this exercise. This is equal to 2 over nt. And that's all there is to it. Take the time derivative and divide by A. So my equation becomes phi double dot plus 6 over nt phi dot plus m squared phi equals 0. This is what we need to solve. You already see this is very easy. As a physicist, the second thing you will do is to eliminate, to make this equation dimensionless. So it's nice to make this equation dimensionless by defining dimensionless time to be time measured in units of the Compton radius of the particle, for example. And then the equation of motion that we have is phi double dot plus 6 over n tau phi dot plus phi equals 0, when now phi dot is defined as d phi by d tau. That's all, no parameters to this problem. And our initial conditions are such that as we take tau to 0, we want the derivative of the field phi dot to goes to 0. This is the type of solution we're looking for. Questions? Yeah?
So, what about the integration constant when integrating A and T? Is it important?
Say it again.
The integration, the constant of integration. When
The constant of integration can be absorbed, I think, by a shifting of time. But
Okay.
you can check more, we can check more carefully later. It is irrelevant for this derivation.
Okay.
Okay?
Okay. Thank you.
It's a good question. Moreover, we want our solution actually to go to a singularity in this hot Big Bang. So we want A at t goes to 0 to go to 0, or to approach 0, as long as the matter content of the universe does what we do. And so we cannot add another constant to that. So in fact, from this sense, you're doing good. Okay, so we have the equation. We can look at the solution of the equation and some consequences. One other thing to say is that in this co-moving frame, for a homogeneous isotopic universe, we can simplify our expression here. And in fact, you can easily check that for this co-moving frame, rho becomes half phi dot squared plus v, and p becomes half phi dot squared minus v. And in terms of our dimensionless parameters and for the potential that we have, I will do roughly here. This is more general than that approximation, but in this approximation, rho becomes m squared over 2 d phi by d tau squared plus phi squared. Squared minus phi squared. And you can check if I made some mistake. So we want to solve this. This is easy. Actually, let me solve this in, well, let me just tell you what the answer is, because this is trivial. Just put it in Mathematica, right? And you can see what you get. The reason I tell you what the answer is because in radiation domination, the output for Mathematica is a tiny little bit ugly. In matter domination, the output is very simple. Well, I can comment about this. So in matter domination, the solution of this equation with boundary condition that phi dot is constant at the time goes to 0 is phi of tau is equal to some initial phi times sinus tau over tau. This is the solution of this equation in matter domination. It's very easy. You can immediately check, plug it back in the equation. So matter domination, right? This is 3. So the 6 over 3 gives you 2 over tau, if you want to check it. For radiation domination, the answer is a little bit ugly. The details of it are not important. So it gives you phi I times a CD number times sine of a CD phase plus tau divided by tau to the 3/4. Both of these things have the following behavior if you plot them as a function of tau. If you're going to plot, sorry, this is the limit when tau is much, much larger than 1. In the limit that tau is close to 1, of course, you can see this doesn't satisfy the boundary condition that I want. It doesn't go to a constant. So that's the limit at large tau. At small tau, it's some hypergeometric function, okay, that is a little bit disgusting. This phase is pi over 8. What's the important point? Both of these solutions do the following thing. They start at phi I with 0 derivative. As tau progresses, look at this solution, for example, right? As tau progresses, what the solution does, it begins to roll down. And as tau grows, the envelope of this field is going to decay like 1 over tau with oscillations. Okay, so it's going to do something like this. At large tau, it's going to oscillate. It oscillates at frequency 1, so it's oscillates at the Compton frequency of the particle. And the envelope decays. So for matter domination, phi, let's say absolute value of tau is proportional to 1 over tau. And in radiation domination, phi of tau is proportional to 1 over tau to the 3/4. Yeah?
So for matter domination, shouldn't it be a cosine to have this behavior you plotted?
You can write it as a cosine if you wanted, but what you get is sine over tau. I mean, so it goes to 1 in the origin. You can change the shift, and this behaves exactly like a cosine at the origin.
Okay.
So it goes to a constant and then decays. At very late time, it doesn't matter how you call the oscillating thing, you see? You can call it whatever you want. Call it a cosine with some phase, and multiply it by a function that has an envelope that is decaying. That is the important point. Once you forget about these little details of the phase in which you're starting, right? What is this solution doing from the point of view of our potential? This solution started its life somewhere here, near enough to the minimum that you don't care about nonlinearities, approximately. And then it started to decrease. So this was, if you want, sorry, this was effectively phi I. Then it started to decrease. It started to go down, you see? And it crossed 0 at some point. With our choice of axis for the field, 0 is just this point, the center of the potential. So it overshot the center of the potential, came back up, and then oscillated back. And it goes on oscillating back and forth with a diminishing amplitude. This is what the solution is doing. Now, it's not diminishing in some completely random way. It's diminishing in an interesting way. And you can see what it's doing. For example, if you go ahead and take this solution, for example, this solution will do exactly the same. You take this solution and you plug it into the expression for rho and for p. That's an exercise you can do. Then what you will see is that the powers of tau in phi organize themselves exactly in the following way, exactly in the correct way, to make rho in both matter and radiation domination, rho of tau, behave like some constant, let me call it rho of I, roughly speaking, the energy density at the time of the start of oscillation, with some order one number that depends, again, on the details of the initial phase and so on. So, but it's roughly rho I times A to the A of tau here to the minus 3. That is proportional to A to the minus 3. Okay? The energy density behaves as follows. It's some constant that dilutes like volume, 1 over volume. Okay? This is exactly what energy density does for dark matter. Okay? Dark matter has the property, a gas of massive particles floating in the universe. If you conserve the number of particles and they have some fixed mass, and you expand the box, the energy density decays like volume, which is exactly what this object does in a rather non-trivial way. Okay? However, unlike a gas of non-relativistic massive particles, like stars that are moving with low velocities, this thing actually has a pressure. I'll erase everything. This thing actually has a pressure. Again, you can compute explicitly for these solutions. So P of tau, it's just the same thing with a minus. This looks like rho of tau, but it multiplies cosine 2m tau. So the pressure is also decaying. It's decaying like the density. But while the density is a purely constant decaying amplitude, the pressure remembers these oscillations that are happening here. That's different. That is a different behavior from a cosmological constant. Cosmological constant had a fixed density and a fixed pressure. They were equal and opposite in sign. This object has a fixed density up to this volume decay and a pressure that's roughly equal, but it has an amplitude that oscillates with twice the Compton frequency. Okay, it doesn't look at all like a cosmological constant, and it doesn't look at all like a gas of slow massive particles because it does have a pressure. Now, non-trivial exercise that I leave to you, and it's very fun. Solve both equations of motion together. Solve the equation of motion for A. For example, in a universe where your phi is actually the dominant contribution of energy density, but it doesn't matter. You can do another exercise. For example, take matter-dominated solution to this one, and solve in parallel to the equation of motion for tau, solve the equation of motion for A, coming from this. So A dot over A squared equal a constant times rho of phi of tau, right? These are two differential equations you can solve. You start from some initial energy density and you solve them. And what you will find is, in the beginning, the metric behaves a little bit funny. It behaves in a way that is not exactly trivial. But after a little bit of time, the metric is going to behave exactly like just a simple dark matter or matter-dominated metric, and you will see that A behaves like tau to the 2 over n In the matter-dominated case, it will be tau to the 2/3. Okay, so basically, this solution is self-consistent. Your dark matter is, or your scalar behaves like dark matter, and the metric behaves like the metric in a matter-dominated universe. Okay, a little bit of an exercise to do. Okay, we are essentially done in constructing a dark matter model from scalar fields. How am I? 15 minutes? Okay, I didn't get to actions, but we can see. We have constructed a dark matter model. What do we need from this model to actually give you the observed dark matter of the universe, for example? If this object is here, the scalar field started somewhere, it's going to oscillate, then what is happening here? So to understand that, we need to look a little bit more carefully at what this solution is doing. And in particular, it's interesting to ask at what tau. I just told you that at very large tau, you oscillate and decay, and at very small tau, you're stuck. What is the value of tau, roughly speaking, that separates this region and this region? Any guess? What can be the value of dimensionless tau that separates them? No guess. Where would you expect? We wrote the dimensionless equation and then erased it. But that describes this motion. It was completely dimensionless. It was phi double dot plus, what was it? 6 over n tau phi dot plus phi equals 0. That's what we did. At what value of this parameter? And this was order 1, right? This was for matter domination. This was 2. What is the value of tau that separates these domains? Throw a number. 6 over n is a valid number. Not 1,000, right? And not 1 over 1,000. It's roughly 1. This is all I wanted for you. I don't really care from this if it is true or 2 or what. It's roughly 1. It's tau over the 1. What does it mean? What does it mean in terms of physical FRW time? In physical FRW time, in this system, it means that tau equal 1 says t of order 1 over m. This object is stuck until the time in this system, FRW of time, is of order 1 over m. However, in the same system, remember, if t is of order 1 over m, the time that takes from starting from 0 for the oscillations to begin, the Hubble parameter, let's call this Tm. It's the t, the variable FRW time that separates these regimes. Well, the Hubble parameter looks like a number over t, right? Maybe this is still written. Here is the Hubble parameter. It's 1 over t. So if t is 1 over m, then your system starts to oscillate when Hubble is of order hm, that's just a name, which is of order m. So a way to look at this object or at this system, I could plot, for example, as a function of scale factor a, I could plot different objects. So let me plot the mass of the particle. For example, in this very simple model, the mass of the particle is time independent, it's just a parameter. So let's put the mass of the particle here. And let's plot the Hubble parameter as a function of a also. So our Hubble parameter is proportional to 1 over t, which is proportional to what? So a is proportional to t to the 2 over n. T is proportional to a to the n over 2. And our Hubble parameter is proportional to a to the minus n over 2. So as a grows, our Hubble parameter in logarithmic units decreases. So our Hubble parameter proportional to a to the minus n over 2. In terms of time, the direction of time is exactly opposite to my plot. So if I will plot the direction of time, it will go from the right to the left. And so, did I reverse something? I want my Hubble parameter to decrease with time. No, it goes in exactly the same direction. Take it back. My arrow of time goes in exactly the same direction, sorry. So A is growing, the time is growing. It goes in exactly the same direction. So very early on in the evolution of the system, somewhere around t equals 0, we cannot really access t equals 0 because there is a singularity here. Hubble parameter is very big, much bigger than m, and our field is spending all this time, all this chunk of time, our field is spending just stuck where it is. Physically, it just doesn't have time to move, right? It's starting to move. It wants to move. But there is not enough FRW time to see it moving. There has not even been a Compton time to see it moving. Okay, so our field is effectively stuck. It just means we are looking at the system in some logarithmic units of this A, and our field just didn't have time to move. When Hubble parameters crosses M, roughly a Compton time has passed. Our field actually begins to move. Once it begins to move, very quickly it goes into this dark matter or matter phase. So we can now try to estimate what is the contribution to dark matter today, or to matter energy density today from this field. Okay, axions will be Q&A. This example is simpler than the QCD axion for a certain reason. So what will be the dark matter density today? A better test, a better way to estimate this is let's calculate the ratio between the energy density of our field at some very late time in the future. Let's choose this time to be the time of matter radiation equality, a time in the Big Bang history that we actually measure pretty well, and divide it by the radiation energy density at the same time, the observed radiation energy density of the Big Bang, and calculate how much this is. So this is roughly, very roughly, this will be omega dark matter, let's call it omega m, at T equality over omega r at T equality, which is roughly, should be a constant. In fact, I don't even need this. I'm sorry. This should be a constant, this should be a roughly 1 if our field gives us all of the dark matter. Let's calculate what this is. Rho phi of T equality is roughly rho phi at the time Tm, the energy density that the field has had over here. At earlier time, the energy density was just a constant. The field was a dark energy, cosmological constant. And from Tm, it begins to decay like dark matter, divided by the ratio of volume between that time and that time, right? So I need to divide it by a ratio of temperature. Let's call one of them. So this would be T equality, and this would be Tm cubed. So temperature is just the typical energy of a photon in this thermal bath. You understand redshift, and you know temperature expands like scale factor. So if I relate temperatures, it's just the ratio of scale factors or the ratio of volume dilution. What do we know about this Tm? We know that the Hubble parameter, if I'm assuming that the universe was, and we see that the universe was, the Big Bang was in a radiation-dominated phase very early on, then this means that at the time that the field started to oscillate in the simplest scenario, the metric is actually dominated by radiation. We live in this picture. Age m, age of Tm needs to be of order m. This is exactly what defines this time Tm. And in radiation-dominated phase, this is roughly just Tm squared over m Planck, the solution of the Friedmann equation when rho is proportional to T to the 4. It's just radiation energy density. So we can replace what this Tm is. This means that our Tm squared is roughly m Planck times m. I don't need any of the details of cosmology. I know life began to be interesting when age was of order m. Good, that's the first thing I know. What's the second thing I know? The second thing I know is that I need to calculate what is rho at the time we started to roll. So what is rho at the end? Rho phi at the end. It's just roughly this initial condition. So it's just roughly the potential. We started to roll with small derivatives in the beginning. So rho was roughly just the potential. I wrote what the potential is. It's half m squared phi squared. So rho m is roughly, I'm ignoring factors of half. It's roughly m squared phi I squared. So this ratio, rho phi over rho r at the equality, is very roughly, let's put that thing. So this is m squared initial phi squared, T equality cubed over m Planck m to the 3/2, right? Take the square root. Divided by the radiation energy density at equality, it is roughly T to the 4. So this is up to a number, T equality to the 4. And we are done with our requirement. Our requirement is very simple. Our model had, roughly speaking, 2 parameters. One of them was a particle physics parameter. The other was a cosmological coincidence parameter. So M was a particle physics parameter. The initial condition was some initial condition where your field started to go, which is typically difficult to predict in the model. It will be some value of the field, somewhere around the landscape at some distance from a minimum, right? And so we can work this out. This says m to the half phi I squared divided by known constant. So T equality times m Planck to the 3/2. And we are basically done with our simplest possible, slightly annoying dark matter model. It's annoying because it comes from some coincidence of where the field started to roll, and it has an unknown mass parameter, but at least one. So effectively 2 parameters for this object. We know these numbers, so T equality is roughly 1 electron volt, give or take a factor of 2, or a factor of maybe 0.3 electron volt. So give or take a factor of 3. M Planck is roughly 1.2 times 10 to the 19 giga electron volt. And if you really want, so these are no numbers, you can just put the numbers here. And so this ratio that you want to be 1, we just found it in our model. It is, if I put the numbers, it's very roughly m over 10 to the minus 21 electron volt. Why not? Just use a reference. Phi I over 10 to the 17 giga electron volt squared times a number that's roughly 1. I didn't do anything fancy. I just put numbers here that some people like to put for this model. Okay? That's it. We got ourselves a particle physics model of dark matter. We can talk about if there is some physical significance to these typical values that you would need to saturate the dark matter energy of the universe, but I put it aside for now. If you want, you can ask. Some people who are curious about it. By assumption, this field is very weakly interacting. Is it easy to make a theory like that? Is it not? I don't know. So we can discuss the physical meaning, but that's it. We made ourselves a dark matter model. Any questions about this dark matter model? That Nicholas will never detect, by the way. You will never detect even if it exists. But there are ways to detect it. That's for another course, if you want. We are trying hard to detect dark matter that is so light and weakly interacting, but it's hard. It does everything we want for dark matter. I have 1 minute to make a very tiny comment about axions. Less than a tiny comment. This was an estimate that we got for the dark matter energy density of some scalar field in a very simple case where the scalar field just started somewhere and its potential is fixed. So, for example, there are no temperature effects that are significantly changing during the evolution of this field. Axion models like the one Christophe mentioned for the strong CP problem, they get their potential essentially from QCD effects that you can think of this as finite temperature effects. Basically what happens as the universe cools, early on in the universe, the potential is very flat, essentially completely flat. So the zero temperature potential for the axion is just flat. If you're stuck somewhere, you're going to stay there up to random fluctuations, okay? But there is no classical evolution, you're stuck. However, the QCD axion develops a potential once the QCD interactions, strong interactions become strong, when the universe cools below about a few giga-electron volt temperature. Then suddenly a landscape appears for the axion, and the landscape is actually something that looks like a cosine potential. So a sequence of mountains, infinite sequence of mountains. And you're going to find yourself somewhere along these mountains. And once you find yourself somewhere along these mountains, the simple picture is you're going to do exactly what I said. The one non-trivial point is that the axion begins to roll at the same time as its potential is forming. And so as the axion field begins to move around its potential, at the same time, the mass parameter effectively is also a function of time. This picture is important. This situation results in the fact that basically the size of the mass parameter of the axion, effective mass parameter of the axion potential, changes by many orders of magnitude between the time that it actually crosses the Hubble rate and the field begins to roll and today. And so there is a non-trivial matching. This matching I did between energy density of the axion at the time of the field at the time it starts to roll to the energy density today. This is modified in a very cute way. And it is, in fact, much smaller. The energy density you get is much smaller than the energy density in this simplest of all models of scalar dark matter. So for the axion, there are some orders of magnitude suppression. It's very easy to compute. If you want, we can do in Q&A, or you can easily do it yourself. But it's smaller essentially by the ratio of the mass of the field at the time it starts to roll to the mass of the field today. Okay, so axions complicate this picture a little bit. Okay, Rogerio, I'm done. I won't, all of this I didn't do. So we started by looking at cosmological implications of particle physics. I, obviously for me at least, only talked about a tiny subset of those, but I think maybe the most striking and maybe in some sense most important ones, but also the hardest ones to solve, okay? I didn't give you any hint that I'm aware of how to solve the question why vacuum energy is not small, but I think I gave us some perspective on this. The vacuum energy today is tiny, but scalar fields, even the Higgs in the standard model, we know, in the context of the standard model, we know that they've moved across distances in field space and in the potential that are tens of orders of magnitude above the currently observed vacuum energy. We know furthermore in the standard model that the vacuum we are at is not even unique. There seems to be another one very far away. Even maybe more striking, the other one very far away seems to kind of bounce over the same point. Why? I have no idea. I'm not sure even how to think on it, but it looks like a clue that we're not understanding. So we discussed this and why Higgs vacuum just metastable. All of these questions make sense in the context of cosmology. Cosmology puts the universe described by this scalar field theory or quantum field theory at a budget of time. It has a finite time scale. It has a finite future. So we can discuss the fact that we're maybe in a metastable vacuum because we've been here for a finite time. Modulo fine-tuning arguments. And I just mentioned a bit dark matter in the context of the same discussion of scalar fields. The simplest modification, if you want, of this kind of picture that we did also contains inside of it dark matter. It looks like any particle physics model you touch can give you a dark matter under some conditions, weakly interacting in this case. All of this is for next time. Thanks very much. It was really a pleasure.
Thank you, Kfir. Questions for Kfir? Yes.
Thank you, Kfir. So how could this field have been created? Do you have any model like, say, baryogenesis or something like that?
Oh, how can you create this field?
Yes.
You don't need to create it, you just need to have it. So how did you create the Higgs potential landscape, if you want? So, right, the Higgs has this vacuum structure. It's a field, so it is, you know, another degree of freedom, 4 degrees of freedom, in fact, that you need to describe reality. It's a quantum field. The theory contains this field. Therefore, the theory contains this structure. So you don't need to do anything to make it, right? You don't need to make the Higgs field. It's a property of space-time, as far as we know. It's another number that we need to give. What it will do now, what the state of the system will do, that is part of the cosmology. We saw for the Higgs field, for example, so the Higgs field starts here and then moves non-trivially because of the fact that our state is hot early on, and the hot thermal effects cause our Higgs field to start here and then roll down. So it already had a non-trivial cosmological evolution. It didn't need to do anything for it. In fact, it would have given you a bit of dark matter if it wasn't that, you know, it was handed over very softly. It didn't just form and fall. It was kind of gradually handed down. And second, it decays. So if you put it there, it will decay. So you didn't need to produce it. The structure is there. Our field needs to be weakly interacting enough that it doesn't decay within the edge of the universe. Not extremely difficult, but the interaction needs to be slow. And that's all, essentially. And it's in initial evolution needs to not come, probably, shouldn't come from this kind of crossover or second-order phase transition that the Higgs had. It wants to have some potential, and then it will just start to evolve, and it will populate the state for you. So what happened to us? What populated this field? You are right in saying that something populated. There is dark matter here. It's actually a gas of slow particles. You can think on it this way. But they are in a Bose-Einstein condensate state. What populated these particles is a bunch of dark energy, basically, or a cosmological constant. So the field had energy density just by virtue of it living in a potential. This mechanism that we saw converts vacuum energy into a gas of particles. That's what it does. That's what this theory is doing. Okay, so this evolution is essentially built in. That's what produced it. Vacuum energy became a gas of particles by this evolution.
Does this model have a fancy name or something that I can
well,
look up?
fuzzy dark matter.
Fuzzy.
So
Yes,
you see,
I've
this
heard.
model is very versatile. We know nothing on it about it, apart from the fact that we've tried the complicated thing, and now the community is driven to this. It's so simple that it's stupid, okay? And in a way. So fuzzy dark matter is the name that people gave when the parameters are in this regime. There is some excitement in the community because this scale looks not so far from the string, or maybe gut scale, so maybe there is this scale. And this very light mass is just what I needed to get the right Rayleigh density. A priori, from theory perspective, anything could be here. You would overclose the universe, or you would have too little dark matter easily. But if you happen to be in this range, then you can calculate that the Broglie's wavelength of particle with this tiny mass, for example, in a galaxy like ours, at the Broglie's wavelength of this is of order of 10 parsec, which is big, it's large. If the mass is a bit smaller, 10 to the minus 22, the wavelength is 100 parsec. 100 parsecs are scale that we really see. This means that there will be deviations from the simple dark matter behavior on the de Broglie wavelength, and there will be this kind of fuzziness from this wave mechanics, basically. It's purely classical mechanics, but it's the wave mechanics of this object. And basically, it's very hard to compress it. And so, hence, essentially, the name fuzzy. What it does, it kind of blurs fine structures in the distribution of galaxies. Nicholas maybe will talk about NFW potentials, you know, the properties that people expect for the distribution of matter in galaxies from simulations. These properties are such that usually it is thought that the dark matter has a cusp profile. It has the density rises very much in the center. If dark matter is this thing, the picture is roughly true probably at large scales, but at small scale it softens the mass. It gives fuzz to the mass. So people call it fuzzy dark matter or ultralight dark matter. So it has a name, but the name is for this silly thing. There is essentially nothing beyond what we did.
Thank you.
Thank you for the lecture. It was really interesting. How would you couple this with matter?
With matter.
Yeah, because kind of you call interaction, and the second question is how far in loop corrections are the corrections that you would introduce? Because it needs to be a really weak interaction, so you need to be contributions in loop corrections, right?
In principle, yes, you could be worried about these loop corrections. But let's start with the size of interactions you could expect. I mean, people have tried to analyze it. But the short answer is that there is not really a solid argument against this kind of field being as weakly interacting as you want. There are guesses about this. Maybe there is some limit on the interaction from the relation to the strength of gravitational interaction and so on, but we don't have some theorem about this. We don't know. In principle, it can be very weakly interacting. For example, for myself, I'm thinking about this problem sometimes, part of my life. And for myself, the regime where the interactions are so feeble that you essentially have no hope of directly finding it is the most interesting for me because you can do it just with gravitation. And in fact, you have a chance to detect the signature of this thing just with gravitation because of the fuzziness effect, because it changes the shape of galaxies by the wave mechanics. There is a lot you can try to do. Now, if you do turn on interactions, then we can begin to try to think. Many interesting things happen. The Higgs field, for example, and you could worry, for example, if the field is somewhere in this regime, it doesn't have to be, right? This initial misalignment can be much smaller, and then the mass can be much larger, in principle. But even if it is in this regime, you can ask, suppose that I add some Yukawa interaction to some sterile neutrinos. I cannot add direct renormalizable interaction to the standard model. But so suppose I add some Yukawa interaction, even renormalizable to sterile neutrinos, then you hit a hierarchy problem. More or less any interaction that you add, if the mass is so small, you're going to hit a hierarchy problem. That is, you would think that loop corrections, you expect them to give a large contribution to the mass. But we already have a hierarchy problem for the Higgs. The Higgs is exactly that. Its mass observed is much smaller than what you would expect given its order 1 couplings to matter and gauge fields, given the fact that there are probably thresholds at TeV or 10 TeV, there are probably more massive particles there, so we already have a hierarchy problem. So here's another one. Maybe it's worse, maybe it's better in terms of the fine-tuning, but it's similar. So there is no obvious theoretical obstruction to this. There are guesses. One thing that will happen, for example, if you couple two particles, there will be thermal corrections to the evolution, and these could affect and complicate what you're doing. And some people are trying to think about this. Some people are trying to play with adding couplings for the sake of being able to see it. You see? So you add an interaction to electrons, for example. You try to make it small enough not to spoil this picture, or complicate the picture but still make the picture work. But the reason you really added this interaction from the theoretical point of view is somehow convoluted in my mind because you do it so you can see it. Okay, so WIMPs, for example, the simplest model of massive particles, the usual picture that we have, people thought we can detect them because the mechanism to make them, the mechanism to populate them depended on those interactions. The mechanism to populate this thing doesn't care about anything. It's just there, it just rolls. It's called misalignment mechanism. All you want is that initially the field is not at the minimum, essentially. So the answer is it's an open area of thought. I gave you by far the simplest case. You can complicate it if you want or if you need.
Okay, and can you kind of make a supposition to identify this kind of extra Higgs singlet or any component of extra Higgs doublet or things like that? This field?
Say it again? Like
make the phi a Higgs singlet. Can I make it?
Well, the way I did it, the simplest case is just a singlet. Why do you call it a Higgs?
Yeah,
if it couples to fermions, or if it couples to some form of new fields, it could give the mass in principle, but I don't have to do it.
Okay, thank you.
Yeah.
More questions? Okay, I don't see any hands up, so let's thank a lot Kfir for this very nice set of lectures. Just a quick announcement.